great pleasure to be here and having Joey to defend his PhD. And just a little memory or history. I remember it was during the pandemic, and Joey showed up in my class, and I think he was very curious. We talked a little bit. Later, I learned that he was planning to go to Singapore, do something. I don't know, it was internship or a job. And COVID happened, and he didn't go. Instead, he showed up in Michigan for whatever reason to do a master's degree. And I have no idea why. And he was very curious in class. He was working in some, something related to registering point clouds and finding relative transformation. It's something that I personally liked and worked on it. He was asking questions. I really liked, what he's working on, and the way he was talking. At the same time, Kira and I had a project, and we had a student, and the student decided that I'm just not going to work on this. I'm going to leave and work. So there was an opening, and Joey was sort of showing around in the class. And then I asked him, do you want to do a PhD with us? And he agreed. So instead of staying 2 years in Michigan, staying, 4 or 5 years, yeah. Which was, I'm sure it was not an easy decision for you to trust us for 5 years of your life. But it was one of the best decisions of my life. Joey, increasingly became independent. He pretty much managed the projects. I offloaded a lot of things on him to just do everything. And the more I gave him, the more he did. And he was good. Unlike myself and pretty much all my students, Joey would get things done way before the deadline. Even his thesis, the papers, 2 weeks before the deadline, there is a paper. And I have to read it. That never happened before. So it's been a really, I think, relatively much less stressful to other PhD students. And I'm glad to be a lifelong friend with Joey, and I'm really looking forward to what he will accomplish after. I think he's going to go to big places and maybe hire me one day. Hire me back when you're very successful. But today, I'm really looking forward to see what you accomplished in the past 5 years.
Yeah, thank you, Mani. Yeah, thank you, Mani, for the kind words. Definitely crazy to think that now I'm actually here. Yeah, thank you to everybody who joined in person and is on Zoom. Yeah, my name's Joey Wilson, and today I'll be presenting my dissertation work on probabilistic deep learning for expressive and reliable world models. So here, we're in the robotics building. We all have a shared belief that robots have the potential to reshape modern life. Some of the ways that they can do this are by replacing humans in dangerous environments, such as wildfires like we saw, unfortunately, in LA. They can also help with healthcare diagnosis and treatment, or my favorite, mitigating tedious activities and increasing quality of life, such as driving your car in traffic, which unfortunately we have to deal with all of the time. Now, in order to make autonomous robots work, they usually require some framework where we take in some data through data acquisition. We use the data to get an idea of the state of the robot within the world. And then from this data, both exteroceptive and proprioceptive, we can create a world model or map. That's what you see in this video, where there are different categories and different colors. We see that there's some sort of Minecraft-based depiction. So there's a geometric representation made up of what we call voxels. And from this information, the robot is able to construct a plan and execute it as it navigates to accomplish the mission within the world. Now, in the real world, that actually is very difficult because the world model needs to encapsulate all of the information that the robot needs in order to act. So this can require very advanced scene understanding. So we can look at these images. One is from an Apple TV show I watched recently where there's some futuristic autonomous indoor robots. The other one is maybe a task we all want to see happen, which is helping to tidy up your room, such as putting away laundry. But in order to accomplish either of these tasks, the robot needs to be able to model the geometry of the environment, the different types of objects, the motion as objects are moving, language, so we can answer from language-based queries from people, and many more. So as a simple example, maybe we want to ask the robot Sunny, hey, Sunny, can you go pour me a glass of wine? So Sunny needs to locate the bottle of wine, decide how to get to it, how to pick up the bottle of wine, a path in order to return. Right? So this is all the information that we need to incorporate within our world model or map. And that's difficult because real-world environments are very complex. This is a video of some data which I gathered a couple years ago. I went to Pittsburgh and got to drive some autonomous or some off-road military-grade vehicles. On the left, you can see the camera views, what we're obtaining from the camera. On the right, you can see the point cloud. What we can see is that the data is sparse. It's noisy. There's dynamic objects that are moving. It can be ambiguous, so we drove by some skeletons, which there's no way we could conceive of that beforehand. We might encounter this type of object. It's also rapidly evolving. So these are all different facets that we need to consider when we are creating our map for the robot. All right, another one is that in the real world, data is sparse. So this could be from sparse data, as we saw with the LiDAR point clouds. It could also be from sparse views. So how do we take this sparse data and use it to construct a more complete representation of the environment? Additionally, in the real world, things are never perfect, right? So we can have some noise introduced by our sensors, maybe downstream from some neural network, which is creating some predictions. So if we know that there are going to be failures, how could we model that in our map so that we can inform downstream applications like planning that there might be not as much information in these regions? So you can see in these images, right, is that the pillows over here are mislabeled. However, we can see that there's high variance or uncertainty, which might provide us a clue for planning that there are some errors potentially in the map. All right. And a recurring theme, which we're going to see, that shows up in my work, is based off of these challenges of real-world data and the types of information we want to incorporate within our map, is finding some optimal balance between probabilistic methods and learning-based methods. So classically, robotics was a very mathematical-oriented, probabilistic-driven field. And the advantages of that are that we can quantify uncertainty, so we know maybe when errors might occur. These methods are interpretable because they're mathematical equations, and reliable because the math underlying all of the algorithms doesn't break down. However, these algorithms can be slow and require hand tuning. On the flip side, recently we've seen the advent of many deep learning-based methods as things like ChatGPT have become popularized due to an advancement in computation. And deep learning-based methods can be very efficient because they can operate in a latent space. They can be optimized using some auto-differentiation, and they can be quite easy to use because people commonly treat these as black boxes. However, they operate in some latent space, which can lead to a difficult time in transferring to other domains. Right, so if we want to consider all of the challenges of real-world data and the advanced scene understanding which we require in an autonomous robot, we need ultimately something in the middle which merges the benefits of probabilistic and learning-based methods. So in this thesis, I'm going to go over 4 different sections. The first one is geometric inference. So how can we leverage the structure of the environment to create a more complete map? The next one is open vocabulary maps. So how do we incorporate language within the map to adapt to multiple different types of categories? We'll also go over dynamic scenes. So how do we incorporate these moving objects within our map for the robot? And finally, I'll discuss information, which is how do we use this uncertainty to decide how to navigate the robot? All right, so the first chapter which I'll go over is on dynamic scenes. And this is the first work which I did in my PhD. And it is exciting, but I'm going to go quickly through this one so I can focus more on the later works, which I want to spend more of the time on. In this chapter, there's 2 main works to talk about. The first one is Motion SC, which is a deep learning paper, and that was my first authored journal paper published in RAL. The next one is dynamic BKI, which is on the flip side, how do we create an algorithm for dynamic scenes using probabilistic methods? All right, so as we discussed, in the real world, objects are always moving. And if we simply combine views, this can lead to artifacts like we're seeing with the white trace left by the vehicle. So then this leads to a question, which is, how can we complete scenes in the presence of moving objects? So as I said, my first approach, which was my first published paper, was called Motion SC. And that was published in IEEE RAL back all the way in 2022. And the main idea here was that we can take some deep neural network, add some temporal information through a finite stack of point clouds to the input, and then use some convolutional neural network to process the data, including how the objects are moving, since we have the temporal data. And then use some completion head in order to reconstruct a full 3D semantic scene. So qualitatively, we'll see in the top right our method motion-SC using 16 frames compared to baselines only using 1 frame of information. And it makes sense that what we see is there's less jittering, right? So there's a lot of noise between frames that we see in the single frame baselines. We also see that using more temporal information helps us to complete more of the environment. So here's a still shot, for example. We can see that the car is driving straight. However, the region to the left is occluded because there's a red vehicle. If we use temporal information, so what we saw previously, it makes sense that we can complete this region of the environment. So this method worked pretty well. However, I faced some difficulties. The first is that I found it was very difficult to actually train a neural network to operate recurrently in these spatiotemporal domains. Right, so that's why I was using a finite number of past frames. Additionally, we saw a lot of noise. There was a lot of jittering. So how do we have any idea when the network may fail? Ultimately, this necessitates some uncertainty quantification or a more mathematical, probabilistic-driven framework. So that's why I turned to dynamic BKI as another paper, which was the complete opposite side of how to attack this problem, which is taking some classical probabilistic method where we know that probabilistic methods hold up recurrently since they're very structured and reliable. And our main idea was that what if we could take information on how objects are moving from scene flow and use it to decay some of these artifacts from cars as they're moving. So I think this is really easy to see qualitatively. On the left, there's a static probabilistic baseline. You can see that there's an artifact left from the car in yellow. However, if we use this information on how objects are moving to decay the trace, we can see that we're able to decay this artifact from the probabilistic method. All right. So in this chapter, we saw 2 different methods. On the learning-based side, we saw motion-SC. On the probabilistic side, we saw dynamic BKI. And ultimately, there were advantages and disadvantages to both. So in the remaining duration of this defense, I'm going to go over the next works which I did, which are how do we take the advantages of the probabilistic and learning-based methods and try to ultimately find some sort of middle ground. All right, so this chapter is representation. So what I'll go over is how do we take the geometric structure of the environment and use it to fill in some of the gaps. So we can see that the point cloud, for example, is sparse. But intuitively, we know that the ground is flat and structures maybe like buildings could be tall. So how do we leverage this information in order to create a more complete map? And in particular, I'll go over 3 published works, all first author. The first one is conv-BKI, which I published in ICRA and TRO. And the next one is an extension towards a framework called 3D Gaussian splatting, which I'll explain later. Okay, so in order to really understand this, I'd like to take a step back and describe the pipeline as a whole. So semantic mapping is a really broad field, but in general, the idea of semantic mapping is that we take some input 3D data. So in this case, it's from some LiDAR point cloud. And we can process it with some algorithm like a neural network, which gives us a categorical belief or prediction for each point. Right? So in here, we see that the blue corresponds to the road. We can see that there's some differentiation with classes like the vehicles and the sidewalk. Now that we have this information, the goal of semantic mapping is to take this temporal data. So as we're navigating the robot, we're obtaining this information sequentially and create a reconstructed 3D semantic map. So in the top right of this slide, we can see a voxelized 3D semantic map. And in the bottom right, we can also capture some uncertainty. So you can see that there looks to be some errors over here. However, we can see that in the uncertainty-based map, there is some red, which means that there is high uncertainty. Okay, so that's a general overview of semantic mapping. And one way which we can accomplish this is probabilistically. So if we're going to accomplish this probabilistically, the first step is to describe some likelihood. So what's the likelihood of some measurement? And since we're operating in a categorical space, the corresponding likelihood which we choose to use is the categorical likelihood. And all the categorical likelihood describes is what's the percent probability that we would likely see some category. So maybe we're driving down the road and there could be a voxel which is 90% road category, 10% sidewalk category, right? So this is ultimately what we're trying to obtain. And one way which we can accomplish this recurrently is using something called a conjugate prior. So the conjugate prior is a tool that we use in order to build up Bayesian inference, and it allows us to quantify uncertainty over this categorical likelihood. So for the categorical likelihood, the corresponding conjugate prior is the Dirichlet distribution. And ultimately, the Dirichlet distribution captures three really key points, which I'm going to go over in a little bit of detail. So the first one is this expectation. So the Dirichlet distribution contains concentration parameters for each category. So going back to that example, maybe we're driving down the road, and there's a voxel where we've observed 90 times that it was road, 10 times that it was sidewalk, right? So 90% of the observations were road and 10% were sidewalk. So that's our expectation, which is this categorical distribution. However, we also have some uncertainty over the belief for this voxel. So the variance term in the numerator encodes basically how different our observations were from each other. So if most of our observations agree with each other, in this case, 90% of them were the same category, we would have relatively low variance. But if we observed that 50% were road and 50% were sidewalk, it would make sense that the variance would be higher, right? We're unsure if it's road or sidewalk. Additionally, the denominator is capturing the number of times we've observed the voxel. So intuitively, if we observe some cell in the map more, it would make sense that there should be lower uncertainty, right? We have more observations, more information. So ultimately, the conjugate prior is encapsulating the expectation, the variance, and the frequency. And this leads to a very efficient closed-form Bayesian update, where since all we have to do for the Dirichlet distribution is keep track of these concentration parameters, it basically leads to a counting sensor model, where all we have to do is keep track of how many times we've observed each category within each cell in the map. All right, so that's how we create this real-time, closed-form, efficient Bayesian update. Okay, but one issue of this is, as we saw previously, point clouds could be sparse. So this could lead to a sparse representation of our map when we combine these frames. One way which people in literature seek to deal with this issue is something called continuous semantic mapping. And in particular, I'm going to focus on a particular solution called Bayesian kernel inference, or BKI. And the main idea of BKI is that we can leverage, instead of just some likelihood, which is describing how points fall within a cell, an extended likelihood, which is saying, let's incorporate also points that fall outside of the cell. So as an example, if we're only considering points that fall within a cell, we would only use this blue point and then update the corresponding category by a value of 1. But if we're using the extended likelihood function, we can also consider this red point, which is outside of the voxel, right? And since, remember, we're keeping track of counts, there is some value associated with this. Previously, it was just 0 or 1. However, now that it's further away, the extended likelihood is also using some kernel function, which describes how much influence these points have over the voxels. So here's an example of the kernel function. This is the sparse kernel function. And what you can see is that when points are right at the center of the voxel, there's a value of 1, which is maximal information. And the further away the points are, that value from the kernel decreases. All right. So people successfully use this method for both occupancy-based mapping, also semantic mapping. But one question which logically arises is, how do we decide what the kernel should be? Right? So it makes sense that we could leverage some information, like the fact that the ground is flat, and maybe objects like poles or towers, as we see in this image, are tall, right? So there should be a lot of influence from this red point on the voxels or cells in the map located vertically adjacent, and not very much on the cells which are located to the sides. So that's the main idea of conv BKI, is that BKI is actually just performing some weighted update, where the weights are these kernel values. And when I see a weighted update, what I think is convolution. And turns out that we can actually rewrite this BKI, semantic BKI update directly as a convolution operator, which means that we took some probabilistic algorithm for mapping and actually rewrote it as a learning-based algorithm. In particular, this is a depth-wise separable convolution. This is because the model basically treats each category independently and then later normalizes to obtain the variance. Right? So depth-wise separable convolutions have a per category shape or kernel, and you might recognize this from the paper MobileNet. Intuitively, again, this matches our expectation, right? We're just learning that things like the ground are flat and things like poles or towers are tall. All right. So since we took this probabilistic framework and rewrote it as a very efficient depth-wise separable convolutional layer, it allows us to have a real-time update at 15 Hertz, including the segmentation network, where we can quantify uncertainty using this conjugate prior. And since the base convolution operator is a very dense function, we use some kind of shifting, sliding window-based approach where the local map moves with the vehicle. Okay. So conv-BKI was our first real attempt at trying to combine the best of these probabilistic methods and learning-based methods. And while it was efficient and very effective, there were some definite limitations. So the first is that it's limited to per category distributions. What this means is all we could learn was that the ground is flat and poles are tall. But what if we're maybe on a slope and the tree or pole is at some angle, right? How do we deal with this? The second is that our network requires accurate depth. We need accurate 3D depth information in order to create the map. Additionally, as I'd like you to see in this the images on the bottom row, voxels may not be representative for indoor scenes because voxels naturally induce some sort of discretization error. So on the driving scenario, maybe this discretization is okay, right? This voxel map looks all right. But if we're looking at this example scene from what we might find in an indoor environment, there's a lot of really fine resolution objects. So how do we create some map representation which can naturally handle that? So that's why I was really excited when 3D Gaussian splatting came out now about a year or two ago. And 3D Gaussian splatting is a new method for novel view synthesis, which means we can take some images, and from these images, learn to rasterize views from any arbitrary view, even something we haven't seen before. What's really unique about 3D Gaussian splatting compared to prior literature is that it represents the world explicitly with 3D ellipsoids, right? So that's what we're seeing in that image. And this is really cool because that allows us to do a lot of operations like what we were looking at in our prior work. And this has really taken, this has been adopted by a lot of roboticists because of the explicit 3D ellipsoid representation and inspired people to try to combine this map with advanced levels of scene understanding, like from semantic information. However, one of the issues which we see is that at unconstrained views, 3D Gaussian splatting can fail without warning, right? So we see a lot of blurring in this rendered image. And similarly, we see some blurring in the semantic categories. So that necessitates some way to combine our probabilistic methods of quantifying uncertainty with this new framework of 3D Gaussian splatting, which is more suitable than voxels for handling these indoor environments. And remember how I said that 3D Gaussian splatting was using these 3D ellipsoid shapes? Well, it turns out that actually 3D Gaussian splatting is a very natural extension of BKI, where in conv-BKI, we were basically also modeling the world as a series of points with some 3D ellipsoid shape. In conv-BKI, we said that the ground was flat and poles were tall. 3D Gaussian splatting allows us to use a different method using some auto-differentiation to actually construct a more maybe complete and involving rotation-based representation. So how 3D Gaussian splatting is working usually is we take some ray and we shoot it through some ellipsoids. And there is some contribution of those ellipsoids onto the color of the ray. So we see the blue, red, and green ellipsoid. Each of those contribute some color, and they have some weight associated with them when we're doing the rasterization. And it turns out that this weight actually satisfies the constraints of the kernel that we were talking about in 3D Gaussian splatting, which means that we can naturally evolve the 3D Gaussian splatting into the BKI framework. How we do that is we just take this kernel, which remember was how we increment the counts in our semantic counting sensor model, those Dirichlet distribution concentration parameters, and we can directly update the number of observations by the alpha compositing, or that like basically kernel value we're obtaining from 3D Gaussian splatting. Okay, so qualitatively, what we see is this allows us to actually first create rasterizations or representations of the environment which don't have discretization error. In order to do this, we basically observe that the rasterized pixels are just some linear combination of the 3D ellipsoids. So we can take the expectation, and then the output pixel expectation is just some linear combination of the ellipsoids that the pixel is passing through. And when we're looking at this rasterization in the bottom, right, there's no longer this kind of Minecraft-looking effect. We can see that actually it's a very fine resolution reconstruction of the environment. Additionally, one of the major advantages of using this probabilistic framework is that we have some variance. So now that we have these concentration parameters on the ellipsoids themselves, there is some variance associated with them. And using the observation that the rasterized pixels are just some linear combination of the ellipsoids, we can also rasterize the variance. So what we see in these images to the right are the rasterization of just RGB, the rasterization using ground truth semantic information, which we expect to look really good. Again, the main difference is it's no longer discretized. In the bottom left, we can see that if we use some off-the-shelf segmentation network, there are some errors which are introduced into our model, right? So this painting no longer shows up, the pillows no longer show up. However, using the variance, we can have some clue that maybe there are some errors. Additionally, we also see that using the temporal smoothing in this table allows us to actually improve the segmentation performance from the input, right? Since we're using multiple frames of data through this recurrent probabilistic framework, it improves over the input. Okay, and here's a video which I think is cool as well. Right, one of the advantages is now we can quantify the uncertainty, and we saw earlier that 3D Gaussian splatting can break down at these unconstrained novel views. So now we see when we're looking at non-training views, the rasterized image in the left starts not looking very good. However, using the uncertainty information from this probabilistic framework, we can actually see some correlation between the high uncertainty areas and the poorly rendered images. All right. So in this chapter, we saw a couple different methods for how we can leverage the structure or the representation of the environment to create a more complete scene. And we finally saw some merging between these probabilistic and learning-based methods. And so far, right, this worked really well, but again, there's always some limitations, always room for more work. So far, all these methods were using the categorical likelihood. And basically, this limits us to modeling a fixed number of categories. So beforehand, we have to decide what are the categories we care about, and we are unable to model any more categories which might show up. This might be sufficient for a driving scene like we see in the bottom left. Maybe we just care about cars and the road. But how would we using beforehand knowledge, discretize the number of categories we see in this indoor image that we might see in the real world beforehand? Right? So that's a significant challenge. We need to be adaptable to whatever we might actually see in the wild. So that leads us to the next chapter, which is on taking the previous methods, which were what we call closed dictionary, using a fixed number of categories, and evolving them to be open dictionary, or handle any category which we might see. And in particular, I'll be going over the paper Latent BKI, which we just published a couple of months ago. And I'll be presenting a little bit at the ICRA workshop, or ICRA late breaking results in a couple weeks. Okay, so that might have gone over some people's heads, so I'm going to start with a video of what that actually means, right? Beforehand, what we saw was we had to choose the number of categories. But now, if we use this open dictionary representation of the map, we can just provide some language-based term, like maybe bed, for example, or microwave. And then we can find the voxels or units within our map which have a high correspondence with this category, right? So now we can actually query with language-based terms, meaning we can generalize to whatever categories we see maybe in the wild. And ultimately, this is built off of the work within the language community. So Again, most people here are quite familiar with things like ChatGPT. Well, all this work in the language community was extended to tie it into some latent space using vision language models. So instead of using a classical segmentation network, there's some jointly vision language tied latent spaces for segmentation. The one in particular we're showing here is called LSEG. And basically now we can take some image, we can provide some fixed number, or not fixed number, any number of categories we want, anything we care about, right? And then now we can categorize the object or the image into these different categories. Okay, so that's ultimately the technology which we want to be able to leverage in order to create our map. That way our map can extend to any number of categories. But that leads to an issue. Before, we were able to naturally just use this categorical likelihood. But vision language models, they're some neural network, and they're also producing predictions. However, these predictions are in are latent space. They're just continuous features. All that these VLMs are doing is they take some image, they process it using some neural network, and now for each pixel, there is some maybe 512 or 1024 dimensional feature, which is in some latent space, meaning we don't really know what it means until we decode the value, right? So a question we have to ask is, what is the suitable distribution for these continuous variables? If we could solve that, then maybe we could take our framework and evolve it to this continuous VLM distribution. So the main idea in latent BKI, which was published in RAL just a couple of months ago, is that conjugate priors can still be applied to the latent space of really any neural network, and in this case, VLMs. In order to do that, all we have to decide is what's a suitable likelihood distribution. Well, since we're roboticists and we're used to working with the Gaussian distribution, that was our first attempt, and it worked fairly effectively. Right? And what's really great about the Gaussian distribution is we know it's really easy to work with, but also since it's the exponential part of the exponential family, it has its own conjugate prior, which means that we can take the same framework from this probabilistic mapping and evolve it into some different conjugate pair relationship. All right, so that's what we see in this framework, is we're still taking in 3D data, process it using some neural network. We use the conjugate prior-based BKI update, and then later we can decode this into the expected category, querying with language as well as some uncertainty. Okay, so for this Gaussian likelihood, there is a different conjugate prior. So basically the normal inverse gamma or normal inverse Wishart distribution. And what I really want to point out here relatively quickly is that the conjugate prior still encodes the same information that we saw in the Dirichlet distribution. So the first piece of information which we see is that there is some expectation, which is really just capturing the running average of the expected features. Before, this was just some running average of the percent number of categories we saw. Now this is just some running average or expectation of these continuous variables. The next one is the variance, so we're just capturing how different are the observations we're obtaining from each other. And in the posterior predictive distribution, we're also capturing the frequency. So how many times have we seen the voxel in our map, and ultimately this dictates the uncertainty, right? So this is very analogous to what we saw with the Dirichlet distribution, and it's a very natural extension into this continuous framework. So now that we have this relationship, this leads to a very efficient closed-form Bayesian update, where now the observations are feature vectors. And we can query them by calculating the cosine similarity with the feature expectation. One challenge, however, is the uncertainty is in the latent space of neural networks. And as I said, in the latent space of neural networks, until we decode these values, we don't actually know what they mean, right? So again, one way that we solved this was looking at other robotics literature. So how do we deal, for example, with these nonlinear Gaussian propagations and Kalman filters? Well, one solution which we tried was using a Monte Carlo approximation, which you might be familiar with from the particle filter. And there's no reason that you couldn't try things like an unscented transform. One downside, however, with this Monte Carlo approximation is that even though it might be very effective when we scale it up to a lot of samples, it can be quite slow. So another solution we tried is using different functionals, which I'll go over later. What I want to show is that there is, again, some correlation between errors in the map and regions of high uncertainty. So this is a real-world example that we did. You can see that there's an upright mattress. And in the second column, these are the predictions given to us by some neural network. We can see that the mattress is very difficult to segment for the neural network. However, by using this recurrent probabilistic framework, we're able to smooth the input so we can still identify that this is the bed category when we query it, as well as that it's a region of high uncertainty, which is shown up in yellow. Okay, now for the last chapter of content, I'm going to go over information. So as the car is driving, for example, maybe it hits a crossroad. How do we decide where to go next? How do we leverage this information we've constructed, this uncertainty we've constructed in our map, and decode that to some information? And specifically, I'll be going over PopGS, which is a paper that was just published in CVPR, and I'll be presenting that in, I guess, about a month now. All right, so taking a step back, we built atop the literature in optimal experimental design, which is something that really shows up everywhere. So constantly, we're dealing with some question of, we have some information, and how do we decide what is the next best solution in order to gain more information? So that might sound really abstract, but as a concrete example, maybe we're trying to test some pharmaceutical drug, right? We already have some idea of how this is working on some patients. But since these trials are very expensive, how do we decide what are the next best or the next most important experiments to run so that we can prove efficacy of our drugs? Additionally, the method we're going to use was actually made by somebody who was doing field work in Greenland, and they just got stuck in their tent for 3 days. And while they were there, they tried to come up with the optimal ways to basically complete their field work so that way they could go home. And in particular, for robotics, the application is active perception. So maybe we're looking for an object. How do we decide what is the next best path to take in order to find the object? Earlier, we talked about 3D Gaussian splatting. So in this chapter, I'm going to focus on how we take a 3D Gaussian splatting model and identify the next best images in order to improve upon the 3D Gaussian splatting model. And one way which we can formulate this improvement is by a reduction in uncertainty. So how do we reduce the uncertainty in our model in order to maximize the information? Previously, we saw a solution which was capturing uncertainty in the categorical space. In this solution, we're now trying to capture uncertainty in the parameter space of these 3D Gaussian splatting-based models. So the parameters in particular are color, location, scale, rotation, and the opacity of the 3D ellipsoids, which again is different from how we captured uncertainty in the categorical space previously. Quickly, I'll go over this, but we used 2 approximations in order to construct the covariance matrix. So the first one, which you might recognize, is the Gauss-Newton approximation. So the main reason we want to do this is instead of constructing the Hessian matrix, all we require is the first-order derivatives, which are really easy to obtain using any like auto-differentiation-based framework, such as PyTorch. Additionally, we relate the covariance matrix to the Hessian, because there's actually an asymptotic relationship in the maximum likelihood estimator for the exponential family. So now that we have this covariance matrix, we rely on the theory of optimal experimental design to capture the next best view, or the way to maximally reduce the uncertainty of the covariance matrix. And in particular, theory of optimal experimental design defines p-optimality, where from some covariance matrix based on different values of p, there's different functions which we can use in order to drive the uncertainty down. And each of these functionals have different geometric interpretations. So for example, here's some covariance matrix, and d-optimality is just saying, what is the volume of the covariance matrix, right? And d-optimality is actually something which widely in robotics literature has been shown to be very effective. In our own experiments, we compare against a uniform sampling and the state-of-the-art Fisher RF baseline. And really similar to prior literature in robotics, we find that t-optimality and d-optimality are extremely effective at coming up with functionals in order to drive down the uncertainty and improve the quality of our rasterizations. We also compare on real data. On the real data, we find an even more significant difference in results. So you can see all of these are actually our method using different values of p. And in particular, for d-optimality, it widely outperforms the baselines on some very common 3D reconstruction metrics. Another application of our method is that we can use it for things like keyframe selection. So for example, given a 3D Gaussian splatting model, how do we decide which images we want to save maybe for training? An example which this shows up in is maybe a 3D Gaussian splatting SLAM, where we're acquiring images very frequently. How do we decide which ones we want to take so we don't take up too much memory? Here we find that t-optimality and d-optimality are very effective, which again matches prior robotics literature. And also another application which I got to talk about with people at my internship at Amazon last summer was basically how we can take this and decide what are the optimal camera views in order to capture some sporting event. So if we can do this, we can actually use technologies like 3D Gaussian splatting to maybe have 10 cameras set up and reconstruct these cool 3D views like what we actually saw in the Summer Olympics, which is what this video is of. And really how we formulate that is, given maybe a model trained on 100 different images, what were the 10 most important views in order to create the entire scene? Okay, so that was all of the content, and I'd like to conclude first with a summary. So we went over a lot of different work, right? And I wanted to make sure that there's some key takeaways. So the first one is that probabilistic methods are not exclusive of learning, right? So sometimes we can think of these as two completely separate types of algorithms. But what my work seeks to show is that we can actually leverage some of the benefits of both and find something in the middle. Second, Bayesian mapping can be directly extended to the latent representations of neural networks, right? So this is something that we saw in latent BKI, that by adopting this Gaussian likelihood, we could take these probabilistic mapping methods and extend them to some neural network hidden space. Third, 3D Gaussian splatting is a very natural extension from the BKI framework. Both are really just treating the world as a collection of points with some 3D ellipsoid shape. And lastly, from probabilistic parameterization, we can obtain expected information gain. One way which we showed that is how do we take this uncertainty in our map and reduce it maximally? For future directions, there's actually a really cool project currently going on in Mani's lab, which is a direct extension from my work, like actually directly evolved from my work based off of working on the ARC project, and that's the DARPA TMAP project. So in this project, what people are looking at is, what if we have a robot that is placed in some new environment and given a prompt, such as, I'm going to the beach, can you help me get ready? How does the robot respond to that query, right? So the first thing is we need to be able to take the language and decode it into the relevant objects. The robot needs to decide where to optimally explore, right? So how do we leverage the uncertainty in the map in order to compute the next best view? And the third is the representation. So what's a really good representation? What are the facets of scene understanding which we care about in order to accomplish this query? Okay, and for future directions, there's actually some based off my work, which I started exploring and I think would be really cool applications for future PhD students. The first one is how do we use recurrent spatial memory with uncertainty in order to create some learning-based algorithms. In the beginning of my PhD, I started off with MotionSC, which was a parallel approach. It was only parallel because I tried recurrent approaches and I wasn't really able to get anything to work. And my intuition is that maybe we could leverage the uncertainty in the model in order to create some recurrent network for spatiotemporal data more successfully. The next one is, how do we create agent-driven approaches leveraging uncertainty for information gain? So we saw a little bit of this in the last chapter, which was using the covariance matrix to calculate the next best view. How do we take these models that I was creating, which capture uncertainty in the map, and use those in order to drive these agent-driven approaches? That's something I'm really curious to see what happens with the DARPA TMAP project. Third, in the real world, maybe as humans, for example, we're constantly using multiple representations. So in my work, I made voxel maps or 3D Gaussian splatting-based representations. But ultimately, we probably want our robot to use multiple different representations. Maybe, for example, image, which is very high resolution, what we're seeing, for example, with our eyes. We also want the robot maybe to have some sort of voxel map capturing uncertainty, for example, what's behind us, right? This could be much less fine resolution, more discretized. And even at a higher level, maybe we want to capture uncertainty in things at maybe the city level. So if we're trying to drive down a highway. And one question which I hope somebody explores, and I really want to see what happens, is how do we take the uncertainty at all of these different levels and try to combine them together so that we can leverage multiple different representations seamlessly. And lastly, one of the limitations of latent BKI and how people are currently tackling this problem is that cosine similarity loses a lot of the reasoning-based capabilities we see of large language models like ChatGPT. So all I can really calculate is what's the similarity between single words. And when we start talking about the question like, I'm going to the beach, can you help me get ready? That becomes very difficult because it requires a lot of reasoning. So how do we incorporate that? And finally, I'd like to close with some closing remarks. And this is something which really emerged from discussions with my committee in the proposal with Ram and JJ. They got me thinking more about uncertainty. And I'd like to say that uncertainty comes in many forms. And it's really just a construct which we use to describe when errors might occur, right? And in this work, there were some very mathematically driven methods to capture uncertainty. But there's no reason that you can't use other methods, that you can't use other distributions to define uncertainty. Because really all we're looking for is when maybe some errors are likely to occur, or maybe how do we relate this uncertainty to information. And ultimately, the choice of metric should depend on the application. So as I tried to show when I was talking about conjugate priors, we were capturing the frequency, the expectation, and the variance of the observations. So I think basically just keep an open mind when it comes to talking about uncertainty. Okay. So yeah, that was all of the content, and now I'd like to go over some acknowledgments. So first, I'd like to thank all of my committee members for all of their help along the way, all of their support. I'd like to thank Mani for recognizing that I had potential in his class. I definitely wouldn't have been here without you, and I really appreciate that. Thanks to Kira also for being there from the start of my PhD and creating like a really warm, I guess, like developing like lab environment. I really appreciate the opportunity to like present with each other and get feedback and be very like development oriented. Thanks to Ram and JJ again for all of your feedback in the proposal. I actually think your comments on uncertainty were really helpful in how I think about it now, and so I'm really excited about the DARPA TMAP project. Also, thanks for letting me work with your students, especially Parker. And here's a fun picture of me with Mani from when we went to IROS in Kyoto. Okay, next I'd like to thank my funding agencies. So the first one was, where I started working was with Mani and Kira on the ARC project. So thank you to them for the funding for the first couple years. After that, something which doesn't show up in my PhD but was really significant to me was teaching. I helped to design the self-driving cars course, the perception part with Minghan. And I also taught mobile robotics, some lectures, both of which are graduate level courses. That took a lot of time, but now I feel very comfortable like getting up here on a stage and just talking. So it was really important, especially also in how I think about problems. And the third one is thanks to Rackham I got the Rackham Predoctoral Fellowship, which made this year a lot less stressful because I don't have to think about money. Next, I'd like to thank all of the robotics and NAME staff for really making this process very seamless. And it helps so much when I don't have to stress about all the things and people are always providing me reminders. I also like to thank the people who work at the Botanical Garden, because going from California to Michigan is pretty tough. And even the last week I went there like 5 times. So it's definitely helped me get through the winter. Also to the graduate certificate for computational neuroscience, all the staff. One of the really cool things about Michigan is we have like so many great programs, and I got to explore them by taking some classes through this certificate program, which I thought was awesome and really shaped how I think about robotic world modeling. I've been really fortunate to work with many amazing collaborators who I've developed friendships with. And yeah, I couldn't be here without all of you. And I'm really thankful to every one of you for all the coffee walks, all of the chats, all of the work which you all have put in and helped me with. Special thanks to the Curly Lab. Really appreciate all the fun times. Look forward to hanging out before I go in about a month. Also to the Barton Research Group. I definitely enjoyed like all of our events. Thanks to Xuan Huan. He's a professor here who doesn't show up. I didn't ever publish a paper with him, but he's who I learned all about optimal experimental design from, and I'm definitely thankful to him for all of our conversations. Last summer I interned at Amazon Lab 126, and it was a great experience. So thank you to all of the people who I collaborated with there, and all of my great teammates and my mentor, Marcelino. And thank you to all of my collaborators. I listed the people who I've worked really closely with, and I've been able to just work with so many more, and I'm really grateful for that. So Anya, Arthur, Jingyu, Josh, Leo, Lu, Minghan, Multi, Parker, Shrey, Shwarya, Srushti, Ela, Yuewe. Thanks to all of you, and thanks to everybody else. I'm really thankful for all my friends. Thanks for sticking by me through this whole process. And I look forward to keeping in touch after. There's so many more people that I wish I could add pictures of. Maybe afterward we can all get pictures. That'd be cool. And then, I'm also really thankful to my family. So thank you to the Wilsons and Muhlsteins for being very supportive. And it was a long way traveling from California to Michigan and being here for 5 years. But I'm really thankful to all of the Muscats and Dominics, who are Jacqueline, my fiance's family, for welcoming into their family and being very loving and encouraging and supportive. It's meant a lot, and I really appreciate it. Thanks to Jacqueline, my fiance. Woo, we did it. And then, of course, to our cute cat, Acorn, with the hat. We have a horse, too. She didn't make the slides. Okay, and then, next for me, I accepted a job. I'm going to start working at Neuro, doing software for self-driving cars on June 2nd, which will be awesome because that's basically what my PhD was on. It was going to be how do we take the data which the self-driving cars are obtaining and use it to create some sort of world model, so the car can act. Okay, that's all I have. Thank you, everybody, for listening. Thanks to everybody in person and on Zoom.